When you think of a mountain range, what comes to mind? Maybe the snow-capped peaks of the Himalayas, or the jagged spine of the Andes. These are titans, no doubt. They scrape the sky and challenge our very sense of scale. But what if I told you the longest, most extensive mountain range on our planet is almost entirely hidden from view? A colossal feature that has shaped our world in ways most of us never consider. It lies submerged beneath the vast, dark waters of our oceans, a silent giant wrapping itself around the globe like the seam on a baseball. This is a story that begins not on land, but in the deep sea. This giant is the global mid-ocean ridge system. It's a continuous chain of volcanoes and mountains that stretches for an astonishing 65,000 kilometers, or about 40,000 miles. Think about that for a moment. You could circle the Earth at the equator 1.5 times and still not cover its full length. It's here, in the abyssal dark, that the Earth's crust is being born. Magma from the planet's mantle wells up, cools, and forms new seafloor, pushing the tectonic plates apart. This process, known as seafloor spreading, is the engine driving continental drift. It's the fundamental reason why continents move, oceans widen, and our planet's face is in a constant slow-motion state of change. A famous part of this immense system is the Mid-Atlantic Ridge. It runs right down the center of the Atlantic Ocean, from the Arctic to the Antarctic. It's the very reason Europe and Africa are slowly drifting away from the Americas, at about the same speed your fingernails grow. In some places, like Iceland, this ridge actually rises above the water's surface, giving us a rare glimpse of this powerful geological process. Iceland is, in effect, a piece of the mid-ocean ridge we can walk on. It's a land of fire and ice, a direct testament to the raw power churning just beneath our feet, a power that has built the single largest geological feature on our world. For nearly 3 billion years, ever since plate tectonics began its grand ballet, some version of this mid-ocean ridge has likely been the longest mountain range on Earth. During the breakup of ancient supercontinents, like Rodinia a billion years ago, or Pangaea about 300 million years ago, the ridge system may have been even longer and more active than it is today. It's a constant of our planet's history, a creator of worlds hidden beneath the waves. Its sheer size and continuous activity make it the undisputed champion of mountain ranges, a true planetary scale phenomenon that has remained largely unseen by human eyes. Now, let's turn back the clock. Way back, about 1.1 billion years into the past. At this time, most of the Earth's continents were grinding together, assembling into a single giant landmass we call the supercontinent Rodinia. When continents collide, they don't just bump into each other. The immense pressure and heat cause the crust to buckle, fold, and rise, creating mountain ranges of epic proportions. The mountain-building event that stitched Rodinia together is known as the Grenville Orogeny. It forged a mountain chain so vast that it would have dwarfed anything we see on land today. This ancient range, the Grenville Mountains, wasn't confined to one continent. Its remnants tell a story of a chain that stretched for over 10,000 kilometers. We find its geological fingerprints, the deeply eroded roots of these once mighty peaks, in eastern North America, from Texas up through the Adirondacks and into Greenland. But the trail doesn't stop there. We find matching rocks in parts of South America and even Africa. These scattered pieces are clues, allowing us to reconstruct a colossal mountain belt that crossed multiple continents before they were ripped apart and rearranged into the world we know today. How tall were these mountains? While we can't know for sure, some geological models suggest they could have rivaled or even surpassed the modern Himalayas. Imagine peaks reaching 8 or 10 kilometers into the sky, creating a formidable barrier that would have dramatically altered weather patterns and climate across the supercontinent. These were not just hills. They were a world-defining feature, a scar left by the violent birth of a new continental configuration. The air would have been thin at their summits, and their slopes would have been subject to unimaginable erosion from wind and rain over millions of years. Today the Grenville Mountains are gone. A billion years of relentless erosion has worn them down to their very foundations. What remains are the metamorphic rocks transformed by intense heat and pressure that once formed the deep core of the mountain range. The rolling hills of the Appalachian region and the ancient rocks of the Canadian Shield are, in a sense, the ghosts of these mountains. They are quiet reminders of a time when our planet's face was dominated by a single landmass and a mountain range of truly continental scale, a testament to the immense power of tectonic forces. Let's journey forward in time, to about 300 million years ago. The continents are on the move again. After Rodinia broke apart, its fragments drifted for hundreds of millions of years before being drawn back together by the irresistible pull of tectonics. This time, they are forming an even more famous supercontinent, Pangaea. And just like before, this colossal continental collision gave rise to a spectacular mountain range. We call this one the Central Pangean Mountains. It was the geological backbone of this new, unified world, a single range running through the heart of a single continent. This mountain chain was the result of the epic collision between the ancient continents of Gondwana, which included modern South America, Africa, and Antarctica, and Laurasia, North America and Europe. The force of this impact was immense, crumpling the continental edges like a car in a head-on crash. The resulting mountain range stretched from what is now the southern United States, through eastern North America, across to northwest Africa, and up through Scotland, Ireland, and Scandinavia. The Appalachian Mountains in the United States and the Atlas Mountains in Morocco are modern-day remnants of this once unified system. Geologists believe the Central Pangean Mountains may have been one of the highest mountain ranges in Earth's history. Like the Grenville Range before them, they were likely as tall as, or perhaps even taller than, today's Himalayas. Their towering peaks would have created a massive rain shadow, leading to vast arid deserts in the interior of Pangaea. These extreme climatic conditions, shaped by the mountains themselves, had a profound impact on the evolution of life at the time. The rise of reptiles, which were better adapted to dry environments, may have been influenced by the very existence of this enormous mountain barrier. Over the next 100 million years, as Pangaea began to stretch and break apart, the forces of erosion went to work on the Central Pangean Mountains. Rain, ice, and wind slowly but surely wore the peaks down, washing sediment into the surrounding lowlands. When you look at the gentle, rounded peaks of the Scottish Highlands or the Appalachians today, you are seeing the deep, ancient roots of mountains that once touched the heavens. They are a shadow of their former glory, but they still hold the story of Pangaea's formation and its eventual demise, written in their very rocks. So, we have these ghost mountains, these eroded stumps of once great ranges. Why should we care? Why do scientists spend so much time studying rocks in places like the Canadian Shield or the Scottish Highlands? The answer is simple. These ancient mountains are like a history book for our planet. They contain a detailed record of Earth's 4.5 billion-year journey, a story of continents smashing together and tearing apart in a cycle that has been repeating for eons. By studying them, we can rewind time and watch how our world was built. It's geology as a form of time travel. When geologists study the rocks that form the core of an ancient mountain range, they can learn about the incredible pressures and temperatures that existed deep within the Earth's crust during a continental collision. They can analyze the minerals and structures to understand the direction and force of the tectonic plates. This information allows us to piece together the puzzle of plate tectonics, mapping out the positions of continents hundreds of millions or even billions of years ago. We can reconstruct supercontinents like Rodinia and Pangaea, not from imagination, but from the hard evidence left behind in these mountain roots. Furthermore, understanding this grand supercontinent cycle is crucial for understanding the history of life and climate on Earth. The formation of a massive mountain range like the Central Pangean Mountains would have drastically altered ocean currents and global wind patterns, creating new climates and ecosystems. The breakup of a supercontinent opens up new oceans and creates new coastlines, providing new environments where life can diversify and evolve. The story of life is inextricably linked to the story of the Earth's geology. You cannot fully understand one without the other. These ancient mountains are a key chapter in that shared story. So, the next time you see a range of old, rolling hills, remember that you might be looking at the weathered bones of a mountain range that once rivaled the Himalayas. You are looking at the evidence of a lost world, a time when the map of our planet was completely different. By learning to read the language of the rocks, we uncover the epic tale of our planet's dynamic past. We see a world not static and permanent, but one of constant, powerful change. And in doing so, we gain a deeper appreciation for the immense forces and the vast timescales that have shaped the Earth we call home.